we are moving on to the next presentation, fracture mechanics, parameters in assessment of high strength concrete frost degradation. Sylwia Borowska is the presenter. Please, Sylwia, the floor is yours.
Good morning to everybody. First of all, let me thank you all for being here today. Before I start, I would like to introduce myself. My name is Sylwia Borowska and I am a PhD student in civil engineering at the Białystok University of Technology. I've got the pleasure to talk about fracture mechanics parameters in assessment of frost degradation of high-strength concrete. My presentation is structural as follows. The aim of the presentation is to describe frost degradation of straight concrete by compressive strength change, mass loss, and durability factor change, and then to compare with the modification of stress intensity factor, fracture energy, and crack mouth opening displacement after 150, 250, and 350 cycles of frost trough. The modern construction industry that aims to create monumental buildings breaking records of high-end span is looking for innovative solutions to use structural elements that are safe in terms of load capacity and resistance to external conditions. Rising land prices in industrialized countries lead to a change in the construction trends, increasingly higher buildings with architecturally complex shapes. Due to the functionality and the economical approach of the building, the main reason for using high-strength concrete is to reduce the cross-sectional dimension of the element. High-strength concrete, despite numerous advantages, are a quasi-brittle material. The addition of steel and basalt fibers to high-strength concrete change it into quasi-plastic material, preventing a sudden brittle fracture in load condition. Numerous publications and works confirm the beneficial effect of adding fibers on the mechanical parameters, but so little attention has been paid to stability of high-strength fiber reinforcement concrete to external environmental factors. Durability is one of the most important parameters describing modern buildings. It has a significant impact to behavior, appearance, usability of the objects. In the process of construction, material wearing out results from the destructive influence of external environmental interaction and improper exploitation. With proper mechanical properties, the durability of the structure under extreme environmental conditions must also be ensured. Concrete not resistant to cyclic freeze-through loses its aesthetic appearance and, what is most important, its strength parameters assumed during the design are reduced. Conventional calculations of structural elements are based on the assumption that the materials are under ideal continuum, have no defects, discontinuities, and change in the structure, resulting from the influence of the external condition. Despite the safety factors used in the construction dimensioning, the results of analysis are characterized by high randomness. Several discontinuities and defects of material may be the beginning of fracture development. High-strength concrete characterized by a rapid increase in initial strength, which leads to the initiation of numerous places with different characteristics of primary deformation. Insignificant in the initial period of existence of concrete elements, discontinuities may, as a result of destructive environmental impact, leads to the catastrophe of the structure. The connection of fracture mechanics parameters with the degree of damage as a result of cyclic freeze-through leads to a more precise description of the integral degradation of high-strength concrete. In my research, I focus on stress intensity factor fracture energy, and crack move opening displacement. This paper presents the results of experimental concerning determination of the resistance to cracking according to the first model of fracture, tensile add bending. The key point here is a durability of high strength and high strength fiber reinforcement concrete. Let's turn to my experimental program. The test was carried out on concrete with a compressive strength of 19 megapascals in order to analyze the effect of addition of fibers to high strength concrete on their resistance to cycling freeze-through. Steel and basalt fibers were used. In all series, constant water-binder ratio was provided. For research concretes was used Portland Cement 1 in amount of 440.5 kilograms by cubic meter. The max grind size of the glacier grid was used to 11 millimeters. River sand of 0 to 2 millimeters grind size was applied. The property of fibers implemented in high-stretch concrete are as follows. Hooked steel fibers and straight basalt fibers, 50 millimeters long. 3 types of samples were made. MBY, high-stretch concrete without fibers, MB2, high-stretch concrete with 50 millimeters steel fibers in amount of 0.5%, and MB3, high-stretch concrete, 50 millimeters long steel fibers, and 50 millimeters long basalt fibers, 0.25% each. Now, I would like to describe sample preparation. During the mixing process, the aggregate was mixed dry with cement and silica dust. Before applying half the water and superplasticizers. When the fibers were added to the concrete mix, the amount of superplasticizers was increased to maintain the consistency of the mix and to prevent the formation of empty space associated with worse networkability. The fibers were added to the concrete mix in stage alternating with a mixture of water and superplasticizers to prevent the formation of hydride fiber clusters. These figures illustrate the geometry of samples for specify the fracture mechanics parameters and the load shame of the test. Test methods used to research durability factors are based on American standard methods. The value of DF factor was determined according to this formula. By the American standards, concrete is considered as not resistant to cycling freeze-through when DF is lower than 60%. In these figures, you can see stands for the resonance frequency measurement and necessary tools and program used. Every 50 cycles, the decrease in high-stretch concrete frost resistance was controlled by measuring the change in the sample's length and modulus of elasticity. The fracture mechanics parameters were determined on the basis of real-time recommendation and the methods developed by Zheng and Shah and the 3-point bending test. The force was applied in such a way that the max load was reached within 5 minutes from the start of the test. The load was carried out by adjusting the displacement of the piston. The crack move opening displacement was performed using a plate extensomer. We can see 2 formulas for stress intensity factor and energy absorbed during the fracture process, and for the research these parameters. The internal fluid rate test by means loss of mass and compressive strength were carried out according to following procedure. The samples were thrown in the water, was frozen in the air, and thrown in the water. Let's move on to the results. The physical properties of high-strength concrete after 28 days of curing are as follows. Water absorption has been increased by about 30% when fibers are added to the cement matrix. Concrete with the mixture of steel and basalt fibers was characterized by the biggest absorbability. The increase in absorbability in the case of the contented fibers in the concrete was caused by a decrease in the tightness of its structures and noticeable loss of bonding basalt fibers in concrete. The presence of fibers in the matrix of high-stretch concrete caused a slight increase in the volumetric density. The conversion of half of the steel fibers into basalt fibers in the MB3 series concrete made it possible to reduce the capillarity pool of ability. This table shows the results of the analysis of stress intensity factor, critical crack tip opening displacement, and the fracture energy. The results show the improvement of fracture energy, fracture resistance of high-strength concrete by adding steel fibers and the mixed fibers. But after 150 fruit rough cycles, a decrease in the stress intensity factor values of concrete with steel and basalt fibers. Concrete with a mixture of steel and basalt fibers has lost its resistance to fracture after 150 cycles of first rough. The value of the critical tip opening displacement in this case is highest. The fibers didn't stop the uncontrolled propagation of the critical crack mouth opening displacement and thus the brittle fracture. In the case of a limited amount of fibers contained in the concrete, it is crucial that they are properly placed in the cement matrix. High-stretch concretes with steel fibers had the highest fracture energy after 250 fruit truss cycles. The fracture energy increased as a result of crack brightening by the most resistant steel fiber and courage. When substantial stress is created as a result of cycling through throw, the amount of fibers used in the concrete becomes insufficient and mechanical parameters become deteriorated. With the increase in the number of fruit rough cycles and the increase in stretch, the resistance of MBY series concretes to brittle fracture increased. This type of concrete, up to 350 fruit rough cycles, didn't undergo the degradation described by the deterioration of fracture mechanics parameters. These figures show the maximum load as a function of the crack mouth opening displacement. The ductile behavior of the MB3 series concrete after 150 fruit rough cycles were shown. The addition of basalt fibers in the cement matrix caused the elongation of the deformation segment until the maximum load is reached. The nature of the work of concrete with the addition of fibers in the cement matrix is clearly changed from quasi-brittle to quasi-plastic, and it is shown by the elongated shape of the MB2 and MB3 series curves in these figures. After 350 cycles, no significant effect of fruit rough was observed on high-strength concrete without fibers. These concretes are characterized by a larger range of elastic deformation, as shown in Figure 1, and at the same time lower resistance to fracture. Due to the more homogeneous structures and fewer voids, MB1 series concrete didn't degrade as a result of cycling through troughs after 350 cycles. None of the tested concretes showed a loss of resistance to cycling through trough, described by a decrease in mass on compression stretch, shown in this table. Concrete with mixed fibers, steel, basalt, after 150 through trough cycles have undergoes numerous cracks, and the modulus of elasticity has dropped by nearly 80%. The decrease in the value of modulus of elasticity after 150 cycles in the case of the analysis high-stretch concrete with mixed fibers corresponds to decrease in the value of stress intensity factor by about 80%. And conclusion of my research, the fracture mechanics parameters of MB2 and MB3 series of concretes improved due to the fibers presented in the high-stretch matrix, but deteriorated with subsequent freeze-thaw cycles. The higher the energy is absorbed during fracture formation, the more resistant the material is to brittle fraction. The addition of fibers to the concrete increased the absorbed energy when the cracks reach the fiber fluid propagation. The cycling through troughs leads to the destruction of concrete with mixed steel and basalt fibers. The fracture mechanics parameters of MB3 series of concrete were significantly deteriorated. Similar critical creek type opening displacement values were observed for high-stretch concrete with mixed fibers and steel fibers before they were subjected to freeze-thaw. This means that the replacement of half the amount of steel fibers with basalt fibers doesn't cause significant change in fracture inhibition. It's important that the steel and basalt fiber volume content of the concrete should be more than 0.5% in order to prevent the propagation of stress fractures caused by the cycling through trough of high-stretch concrete by crack-brightening the fiber properties. The frost resistance of high-stretch concrete is associated with absorbability. The presence of fibers in high-stretch concrete significantly increases their absorbability. Steel and basalt fibers in concrete can withstand tensile strength, reducing the formation of cracks and limited stress concentration at the tip microcracks, preventing them from spreading, thus eliminating the formation of combined crack. However, special care must be taken to ensure that the fibers are correctly distributed in the concrete mix, and a proportionally higher number of fibers must be used to prevent the propagation of future fracture formation that occurs with the subsequent freeze-thaw cycles. The decrease in the mechanical properties of concretes with fibers was also caused by a decrease in the adhesion of the basalt fibers to concrete due to the loss of the continuity of the fiber's outer coating. Cycling through trough in the initial phase contributes to the increase of fracture energy. However, as the frost degradation process, the fracture mechanics parameters deteriorate. The increased absorbability of high-strength concrete with fibers resulting from poor regions leads to a concentration of tensile strength in these areas as a result of cycling through trough, and as a consequence to internal degradation of the concrete. Thank you very much for your attention. It was a pleasure being here today.
Thank you very much, Sylwia, for your presentation. Now it's time for discussion. You have some questions already. Please read the question and answer the question.
Please was the distribution of fibers within concrete examined. MBY series of concrete, the distribution of fibers in the concrete matrix was in section to prevent formation of the clusters. In the case of fiber reinforcement concrete, the fracture process zone is larger than in a classical concrete. Did you evaluate this fiber FPZ and compared it to the size of your samples? I don't evaluate it. In the next stage of my research, I compare the process zone of the. fiber reinforcement concrete.
For the moment, we don't have more questions. Motohiro, do you want to make a question or comment?
Yes, yeah, actually, I was also interested in fiber dispersion. I think you use very low W by V, like 31%, I think, and add fibers. And do you think it was very tough to mix the materials? The mixture was very thick, viscous.
Mixture seems to be thick, but I think it's problem with the coating of the basalt fibers in the mixing process.
So if fibers are not well dispersed in your specimen, you may have big errors, variations in your experimental data. So that's a point of question from Brima, I think. And another question is, in your data of MB2 case, after 150 FT cycles, the fracture toughness, if I remember correctly, decreases, but after 250 it increases, and after 350 it decreases again. So the data is kind of like fluctuating. I may have missed what you say, but could you explain why that was the case?
It can be that the steel fibers brighten the fracture propagation, and in the samples with steel fibers placed in the propagation of fracture, it is brightening them, and then the fracture energy was larger, bigger.
And sorry, how many specimens do you have for each case?
For each case, I have four specimens.
4 specimens, okay. I see. If you have weird trend in your data, it might have been caused by some, not so good experimental setup, the guy mentioned in the fraction process stones or something like that. So maybe you may want to check the, accuracy of your testing method or something. Thank you. Looks like we have one more question in the chat.
Yes.
Did you think that the addition of fibers modify the stability of air bubbles network? Why do you use the 42.5 cement type? I think the addition of fibers modify the stability of air bubbles networks. It modify a structure that bubbles were large amount of air bubbles, and they are smaller. I use 42.5 cement type because it's the most popular type of cement, and used for high strength concrete. And the variability of the results is quite high for MB3 and 100 ultra cycles. Is there an explanation? Yes, modulus of elasticity for 100 ultra cycles were examined, and by this period of time, it's it's not that's so worse, but its value be lower than 80%. After 100 cycles of fruit thaw, we have 40% 40% of the DF after fruit thaw.
You have another comment now? It's more a comment than a question, I think.
It would be interesting to characterize the air bubble network. There is many methods to do it. I think in the next stage of my research characterize that.
Okay. Is there any other question? If not, thank you so much, Sylwia, for your presentation. And I think we are at the end of our session. Is that correct, Farid?
Yes.
Okay. So we are going to close the session, but I would like to ask Motohiro if you want to give some final words to the participant of this session.
Well, yeah, thank you so much. Actually, I really enjoyed presentations of this session. I think all of the students are doing very good research. So I hope all of them will successfully finish their PhD study. Thank you.
Okay, it was also a pleasure for me. Thank you very much to all the speakers. They were 3 ladies, and their presentation were very interesting. It's very interesting to see how we have good, promising young people to participate in FIB in the future. Thank you very much to the audience, because the main goal of this symposium, PhD symposium, which is organizing since more than 26 years or something like that, was to attract young people and to give them the possibility to have a presentation with some more time like usually, and receive inputs, comments, and questions from other people. This is very important to open our findings to other people, and this was the goal of FIB, and we are doing very well. I'm happy to hear that the discussion were very interesting. Thank you very much to participate and to make questions. And last but not least, I would like to thank the organizers of the FIB PhD symposium. We have the conference was very, very interesting. I had the opportunity to participate in some sessions. And I would like to thank also my young co-chair, Motohiro, Thank you so much for your assistance. And I would like finally to thank also the team from FIB who is working from Switzerland, and they are always very attent to help us. So I hope you enjoyed the session. I'm happy to see that the organization of this type of FIB symposiums is still very useful for young engineers, and I invite you all young engineers to participate and collaborate in FIB. We really need you. Thank you so much.